A very good evening to all dearest participants, research scholars, young and vibrant minds of today's generation. On behalf of Light Wave Communication System Laboratory, myself Subhash Arya, Associate Professor and in charge of Light Wave Communication System Laboratory, Department of Electronics and Communication Engineering, NEU Shillong, would like to heartily welcome you all in the third reading session of PhD thesis entitled Design of Directional Coupler Based Silicon Optical Modulator, submitted by Mr. Himanshu Ranjan Das in my supervision for the award of PhD degree in Electronics and Communication Engineering, NEHU Shillong. In the last two reading sessions, Mr. Himanshu has read first two chapters of the thesis, that is the introduction, in which he has covered introduction to optical communication itself, then literature survey of optical modulator, particularly plasmonic material based optical modulators, followed by the motivations and objectives set in thesis to carry forward the research, then problem formulation, scope of research has been depicted, then major contribution of the thesis, significance of the research outcomes, and lastly organization of the thesis were the main content in chapter 1, that is the introductory chapter. About 20 participants have participated on that day, on very first day. On the second day, chapter 2, we have covered the title Electro-Optic Modulators. It consists of introduction, then electro-optic effects such as electro-absorption, carrier density effects, linear electro-optic effect, Kerr effects. After that, what are the various kinds of optical losses like absorption, scattering, and radiations were discussed and read. Performance matrices of optical modulators such as insertion loss, extension ratio, energy consumption have been discussed and read. Types of various optical modulator such as silicon high-speed modulator, electro-optic polymer-based modulator, complex oxide electro-optic modulator, and gallium arsenide modulators were in principle briefly were discussed. After that, a detailed mathematical modeling of directional coupler-based optical modulators were done. Then applications of modulators in beside optical communication, how we can use in other field also has been discussed. And then finally, with summary, it was concluded yesterday. You know, this reading of PhD thesis, which is a very rigorous task, sometimes a monotonous work. It is not so interesting. So that is why we thought, let us come together, read simultaneously, and discuss it so that we can make it more interesting, more attractive. And the task, which was really uphill task, can be very easy. I feel very happy that in 2 days we have covered 2 chapters, which was not possible otherwise, unless you are very, very motivated or some task has been assigned to do so. So I would like to thank you again who have spared their valuable time to join virtually in this PhD reading session. Please feel free to interrupt at any place, anytime, if you feel that clarification should be given. So we shall be very happy. This is a not a very formal session. Let us make it informal session. Let us open your mind, try to involve it, try to walk through us. This work has been completed in last 6 years by Himanshu Ranjan Das. with his very dedicated. He sacrifices a lot while carrying forward this work. So in order to appreciate his work, in order to recognize his work, of course, you know, this thesis is going to give him the highest degree and allow him to put doctor against his name. So you know the value of this PhD, but this document, which is after a few days, it will come into public domain. We are so fortunate that we are getting chance to read it line by line, as well as a department. If some you, I think this is a kind of unique activity in order to develop, in order to create a good environment, good research environment, to motivate our young generations as well as newcomers who are going to join research in general, as well as our laboratory, light wave communication system laboratory in particular. With this, without taking much time, I would like to invite Himanshu. Please go ahead. Yeah, before inviting, let me tell the chapter 3. What are the different titles? So chapter 3 is basically a contributory chapter. It consists of publication of one SCI index journal publication, that is the Journal of Optics. So this chapter consists of introduction of various architecture design, then plasmonic material. We are going to characterize what is the basic characteristics, optical characteristics of plasmonic material. Then what methodology have been adopted to carry forward this particular research outcomes, such as finite element method and finite difference time domain method. Then directional coupler based optical modulator, its working principle, design, material characteristics of indium tin oxide, and the resultant discussion. After that, in section 3.5, modified side wall angled silicon waveguide based electro absorption modulator were extensively discussed. Basically, there was already a published work on some side wall silicon waveguide based electro absorption modulator. So we read it, we identify the shortcomings of that published work, then we try to improve. So there we extensively simulated what is the optimum side wall angle, so that we can improve the performance of existing modulator. Of course, this was a incremental work, development work, but it could find a place in a reputed journal as a research outcomes. So over to you, Himanshu. Thank you so much for your patience.
Thank you, sir. So today we'll be reading the chapter 3 of the thesis, and the title of chapter 3 is Architectural Design of Silicon-Based Optical Modulators.
Hold on.
So
Let me come on chapter 3, because this was the abstract. Then content we read, and after that, I hope screen is visible.
yes, sir.
And it is enough large to see the text. So this is the chapter 1, introduction, then literature survey, and after that, motivation and objectives, scope of research, major contribution of the thesis, significance of research outcomes, and organization of the thesis. This was the content. Then followed by chapter 2, electro-optic modulators, introduction, electro-optic effects, plasma dispersion, Kerr effect, losses. Then after that, this was the performance matrices. 3 performance matrices basically we have covered. Then types of different optical modulators. This is application of modulator and this summary. Now this is the title of chapter 3, architectural design of silicon based optical modulators. Yes, over to you, Himanshu.
So let us begin from introduction. In this chapter, the architectural design of plasmonic-based optical modulators, plasmonic material properties of indium tin oxide, and the performance matrices of the device are discussed. Also, the methodologies used to carry out the operation of the device are discussed. The optical modulator's design plays a significant role in enhancing/degrading the performance of a device. Therefore, proper utilization of the device dimensions is needed to get optimum device performances. In this chapter, the working of a directional coupler-based silicon optical modulator and an ITO-based modified sidewall angle electro-absorption modulator are discussed. The section 3.2 Plasmonic Materials. Plasmonics is an exciting field of research because of the promise of new materials capable of reference 18 and 43. Point number 1, exceptional optical properties such as confining and guiding light for sensor and computing applications. Next point, plasmonic material based electro-absorption modulators are compatible with CMOS technology. The next, plasmonic materials are index modulated materials. That mean the properties of plasmonic material changes upon introducing an applied potential. Next point. Also, plasmonics enables synergy between electronic and optical components. Exhibit tunable optical absorptions due to the collective resonant oscillation of the free electrons in the conducting material to respond to the incoming illumination. In this thesis, mainly two plasmonic materials, ITO and VO2, are discussed. Other plasmonic materials like gallium zinc oxide and graphene are beyond the thesis scope. ITO is a ternary composition of indium, tin, and oxygen in different proportions. Reference 44. It is a transparent and colorless in thin layers, while in the bulk form it is yellowish to gray. It is widely used as transparent conducting oxides because of its electrical conductivity and optical transparency, and the ease with which they can be deposited as a thin film. The optical characteristics of ITO will be discussed in this chapter. VO2 is an inorganic compound and it has a phase transition very close to a temperature of around 66 to 75 degrees Celsius. Reference 45. The properties of the material like electric resistivity and opacity are used in memory devices, phase change switches, and aerospace communication. Coming to section 3.3 methodologies. The design of photonic devices usually requires an understanding of how the light propagates through the structure. Most devices include a variation of the structure as the light propagates, leading to numerous phenomena like reflection, interference, scattering, and radiation. The interaction between multiple modes and changes in the mode profile. Many techniques and methods like the beam propagation method, transfer matrix method, eigenmode expansion method, and finite difference frequency method were developed to solve these problems. Reference 46. However, due to the complexity of the waveguide structures, the most general and rigorous approach used are the finite element method and the finite difference time domain method. In our work, we have primarily used the FEM method to solve the problems related to simulation. Section 3.3.1 Finite Element Method. The finite element method FEM, a numerical method for solving partial differential equation for steady state problems. Inside the bracket, no time variation, is a widely applied optical waveguide design method. Reference 47. FEM divides the computing area into numerous subdomains, that is mesh, and the final numerical results are obtained by gathering the ones of each subdomain. Figure 3.1a shows the mass graph of a 2D electro-absorption modulator in a commercial FEM software console multiphysics. Reference 48. And figure 3.1b shows the numerical simulation of the supported fundamental mode by setting each layer's material parameter, the geometrical parameters, boundary conditions, and the modes supported by the proposed waveguide can be found. So here in figure 3.1a and 3.1b, it shows the cross-sectional view of an optical modulator. So figure 3.1a shows the mesh structure, how the device is subdivided into various domains. So in FEM, what used to happen is that each domain is calculated separately, and at the end, all the domains are combined to get the result or the output. So the final output is shown in figure 3.1b. And the division of the device in various domains is known as mesh. So coming to section 3.3.2, finite difference time domain. The finite difference time domain FDTD method is a numerical method to solve the time-dependent Maxwell equations. Reference 49. The partial differential equations are divided into space and time derivatives, and the space equation are solved at a given instant time and then at the next instant in time until reaching the user-defined FDTD computing time or terminal conditions. FDTD operates in the time domain. FDTD simulates the propagation of a pulse of light tends to 100 of femtosecond long, which contains a broad spectrum of wavelength components. Reference 50. The system's response to the short pulse is related to the transmission spectrum via the Fourier transform. The disadvantage of the FDTD technique is that it is computationally intensive since the simulation time step is femtosecond. However, the algorithm scales well to multiple processor and compute cluster simulations. Thus, the simulation volume and accuracy can be improved with additional computing resources, including graphic processing units, that is GPUs.
So, Himanshu, we can give a pause if any participant has question regarding this. So can be asked. Methodology, plasmonic material, and introduction. Three things we have covered. So in brief, to plasmonic material are epsilon near zero material, ENZ. Then two types of material have been used in this work, that is the ITO and VO2. And further, as far as methodologies are concerned, researchers have come up with various types of numerical simulation method, that is beam propagation, transfer matrix method, eigenmode expansion method, FDDT, and so on. So here, since we are using a commercial software that is called COMSOL Multiphysics, which was funded by DST SERB under the Young Scientist Project. So that is why we are a kind of bound to use that FEM method of simulation using COMSOL Multiphysics. So in COMSOL Multiphysics also, though two modules were there basically, since it is related with uh, some material property, then wave optics and semiconductor physics. Three modules have been extensively used while simulating the structure. So here, wherever we have a transition, as far as this figure 3 is concerned, you see here, this is the basic structure, and in this you see the finite number of elements. With small elements are large in number, because at this, we need more accurate information compared to this at boundaries. Okay, so because there is less information is available, that is why this element size is bigger. However, we need minute information, that is why the element size is very less. So it is a structure dependent mesh has been used, and there is a condition of choosing the size of mesh. It is basically wavelength dependent. So whatever the light we are going to pass through this structure, based on that it needs to be. So it determines your accuracy. Unless you select an optimum mesh size, your result may be incorrect. Okay, and this is the field intensity distribution in the structure. So you can see here the actually it has been shown here also the color bar graph. So blue color must be here, then red color must be here. Okay, and then blue this white or something like that. This color spectrum will tell that is intensity of the field distribution. Okay, so yellowish color means intensity of light is higher here at the center of this waveguide. However, if we go away from this device structure, intensity of light is not. So confinement of light through the waveguide is highest. Uh, this is the meaning of this structure. And as a researcher, it's our job to determine the optimum structure or optimum design so that maximum light can be passed through this waveguide. Okay. And yeah, this is finite difference time domain with FDDT. We have seen this Maxwell equations are solved in time base and femtoseconds pulses are used. So advantage is that it gives accurate value. However, it needs high computational efficient machine, as well as it requires more time also. But since this FDDT is not available in COMSOL multiphysics, that is why we were not able to use. However, through openware software that is available through MIT, one can use it. So with this, any question, participant can write the question in chat box also. I will take up in case. If no question, then I would request Himanshu go ahead.
Okay, sir. So coming to section 3.4, directional coupler-based optical modulators. Introduction. Directional couplers are used to couple energy/light from one waveguide to the other in particular directions. Directional couplers can be used as power splitter or power combiner depending upon the operation it performs. Reference 42 and 46. The coupling between the waveguides in the directional coupler can be explained by the CMT, that is couple mode theory, which is explained in chapter 2. The directional coupler consists of two parallel waveguides, where the coupling coefficient is controlled by both the length of the coupler and the spacing between the two waveguides. In silicon photonics, directional couplers can be implemented using any type of waveguide structure, including rib and strip waveguides. Section 3.4.2, Design of directional coupler-based optical modulator. Due to the ongoing demand for huge bandwidth, high-speed computing, and low power consumption, numerous SI-based photonic devices have been developed to date, like microring resonator, Mach-Zehnder interferometer, microdics, etc. Reference 46. These devices use the relative phase shift between two traveling waveguides, which are based on tuning the refractive index of silicon through the introduction of an electrical signal. Reference 51 and 52. But these devices suffer from narrow operation bandwidth and comparatively high power consumption, which makes it less reasonable for high modulation bandwidth, low power consumption. Therefore, in order to achieve a high modulation bandwidth with low power consumption, directional coupler-based silicon optical modulators are being modeled and developed. The design of the directional coupler-based optical modulator is shown in Figure 3.2, where the cross-sectional view of the device is shown in Figure 3.2a and the top view of the device is shown in Figure 3.2b. The device consists of a metal oxide semiconductor type hybrid structure. ITO is sandwiched between two SI waveguides separated by 5 nanometer HFO2 on both sides, as shown in Figure 3.2. The center consists of a ITO-HFO2 interface structure that allows us to configure a MOS-type waveguide structure. The width and the thickness of the silicon waveguides are denoted by WSI and TSI, with WITO of ITO equal to 190 nanometer WSI equal to TSI equal to thickness of ITO equal to 300 nanometer. The waveguides are placed upon silicon dioxide SiO2 substrate. Both the Si waveguides are connected to an external electrode ground placed hundreds of nanometer away as shown in figure 3.2a to have a negligible effect on the mode profile. The electrical signal is applied to the ITO block. Figure 3.2b shows the top view of the optical modulator where the input is given to the longer SI waveguide which couples with the shorter waveguide crossport and the output comes out of the same waveguide throughput port. The intensity of the guided mode attenuates when the signal couples with the ITO-HFO2 interface. Also, the device can be realized using conventional semiconductor fabrication technology. The silicon waveguides can be formed using an E-beam lithography process on a SOI platform followed by dry etching of silicon down to the buried oxide, that is SiO2, reference 51. Also, the silicon waveguides are coated with a thin layer of HFO2, hafnium dioxide, using the atomic layer deposition technique. ITO can be deposited between the SI waveguides by using a standard RF magnetron sputtering machine, reference 51 to 54. A commercial finite element method solver FEM console multiphysics is used to carry out the simulation. Now coming to section 3.4.3, material characteristics of ITO. ITO is a plasmonic material. The refractive index of ITO changes upon the application of applied potential, which is dependent on its permittivity. The wavelength dependent permittivity of ITO can be calculated from the Drude-Lorentz model, reference 11, where epsilon r equals to 3.9 is the high frequency
Please
permittivity
read
of
this
ITO.
equation. Please
Yeah,
read this equation, very important equation. Epsilon r.
epsilon r equals to epsilon infinity minus omega p square divided by omega square plus j gamma omega, where epsilon r equals to 3.9 is the high frequency permittivity of ITO and gamma is the electron scattering rate equal to 1.8 into 10 to the power 14 radian per second. The angular frequency and the plasma frequency are denoted by omega and omega p, which is dependent on the variable n, carrier concentration of electrons, reference 8 and 15, and is calculated as omega p equal to root over n e square divided by epsilon naught into m star, where the electron charge is denoted by E. Epsilon naught is the free space permittivity and m star equals to 0.35 m naught is the effective mass of an electron, where m naught corresponds to the electron rest mass. Also, the electron concentration N is directly proportional to the applied potential and is calculated as reference number 8 and 11 n equals to small n naught plus epsilon naught into KHFO2 into Vg divided by E into THFO2 into TSCC, where Vg is the applied potential and N naught is the bulk free carrier concentration of electrons under zero bias gate voltage, reference 11. The KHFO2 equals to 25 is the permittivity of HFO2, reference 11, and THFO2 is the thickness of HFO2 layer. The accumulation layer thickness is denoted by TACC. Now, for the directional coupler based optical modulators shown in figure 3.2, the THFO2 equals to 5 nanometer, TACC equal to 1 nanometer, and N naught is equals to 1 into 10 to the power 25 meter cube. Reference 6. Therefore, The complex permittivity of ITO is shown in figure 3.3a, and the change in carrier concentration as a function of applied potential is shown in figure 3.3b. From figure 3.3a, it can be seen that the real part of ITO's permittivity, that is Re epsilon subscript ITO, decreases, and the imaginary part of the permittivity in, increases with increase in applied potential, and the Re epsilon subscript ITO reaches 0 at Vg equals to 2.3 volt. At this potential, the phase of ITO changes from a pure dielectric to a metallic state. This is termed as epsilon near zero condition, ENZ, reference 6. Also, with an increase in potential, the N increases as it is proportional to Vg from equation 3. Therefore, Vg equals to 2.3 volt corresponds to N equals to 6.4 into 10 to the power 26 meter cube.
Yeah. So before moving to results, any question? Basically, we can see three questions. Can you hear? Yeah, just a second. So basically, see here we apply a voltage to the structure, so which changes your carrier concentration. This carrier concentration will lead to change in this plasma frequency, and then plasma frequency will lead to change to optical property, that is the permittivity. And there is a relationship between permittivity and refractive index. This is how, in nutshell, we can see. Apply the voltage, carrier concentration will vary. Carrier concentration variation will lead to change in the plasma frequency. The plasma frequency variation will change into the this permittivity, relative permittivity. So this is the basic modeling, and through this diagram we can see uh, at particular voltage we have to optimize this voltage at what voltage carrier concentration should be selected, and based on that we can see there is an increase uh, in the imaginary part, that is the loss, a decrease in the real part of refractive index, which changes basically phase with respect to increase in the voltage. So that is the relationship. So that is a kind of characterization of your plasmonic material, ITO. So first of all, whatever material we are going to use, uh, we have to characterize it, understand its basic principle. Then only we can go for using it as optical modulator. Stop here. If any question is there, please one can either unmute your microphone, or you can write your question in chat box. So, Himanshu, go ahead.
Okay.
No question there.
Coming to section 3.4.4, results and discussion. The characteristic of ITO HFO2 based silicon optical modulator is dependent on the refractive index of the waveguide. The normal refractive indices of silicon dioxide in HFO2 has been considered 1.44, 3.47, and 1.98 respectively. The refractive index of ITO can be calculated from the wavelength dependent permittivity of ITO as shown in figure 3.3a. Now, the imaginary part of refractive index corresponds to loss. With an increase in Vg, the real part of ITO's permittivity decreases and the imaginary part increases, governed by equation 3.1 as shown in figure 3.3a. Also, the concentration of carriers increases from 1 into 10 to the power 25 meter cube at Vg equals to 0 to 6.4 into 10 to the power 26 meter cube at Vg equals to 2.3 volt as per equation 3.3. At Vg equals to 2.3 volt, ITO reaches ENZ condition. The intensity of the electric field as a function of applied gate voltage at Vg equals to 0 volt off state and Vg equals to 2.3 volt on state is shown in figure 3.4a and b respectively. The coupling length LC of the waveguide can be calculated from LC equals to lambda by 2 into n symmetric minus n antisymmetric equals to 10 micrometer, where lambda equals to 1550 nanometer is the operating wavelength. N symmetric is the symmetric mode refractive index, and N antisymmetric is the antisymmetric mode refractive index, and N symmetric minus N antisymmetric equals to 0.0775, reference 651. The length of the coupler can be calculated from L equals to 2 into LC equals to 2 into 10 micrometer equals to 20 micrometer. The
Himanshu, can
transfer,
you explain this figure 3.4,
yeah.
before going to result? Yeah. This is the
So
waveguide one. Yeah.
coming to figure 3.4, 3.4a shows the intensity of the electric field at off state. Means whenever no potential is applied to the ITO layer, that is sandwiched between the two SI waveguide, what happens? Light is coming whenever a signal is introduced to the waveguide, then it tends to couples with the waveguide which is standing next to the waveguide. That is, it tries to couples, the energy couples from one waveguide to the other. So at a coupling length which is written in the text LC. So when LC exceeds, that is when the LC, that is the coupling length, exceeds twice in length, that is 2 into LC, which is here 20 micrometer, then what happens is that whenever it again couples back to the same waveguide, it again couples back to the same waveguide whenever no potential is applied. However, when a potential is applied due to the characteristic of ITO, some amount of energy is absorbed by the ITO layer. So then what happens is that when the light is traveling from one waveguide to the other, it doesn't couples back and comes out from the same waveguide. So it will come from one waveguide and it will go through the other as shown in figure 3.4b. Whereas when no potential is applied as shown in figure 3.4a, the energy will travel from one waveguide to the other and again it couples back to the same waveguide from where the input signal was introduced. So this is the phenomena that is shown in figure 3.4a and 3.4b.
Himanshu, can you tell where is the input and where is the output?
So the input is in figure A 3.4a. The first waveguide is the input.
Upper one. You mean to say
Yeah,
here,
upper
upper.
one. Yeah.
And where is the output?
Output is the very end of the same
This
waveguide.
same.
Yeah,
Okay, this is the
yeah,
output. But you are telling that, see, if you give the light, light is coming. So how it
yeah.
is off state?
Yes, sir.
How it is written here off state now?
Yes, sir.
So how it is off state? Because when you said the light is available here
Yes,
at the
sir.
output. So then how it is off state? Why not it is on state?
Sir, in directional coupler, what happens is
Oh,
that there are two waveguide. So
okay, yeah,
where 0 volt corresponds to off state and
okay.
2.3 volt here corresponds to on state. So in if we see in figure this in waveguide number 2, if we see, if we compare waveguide 1 with waveguide 2, whenever an potential is given,
Hmm.
that is 2.3 volt, then the signal will come out from the second waveguide.
It means this on state means electrical signal. When you apply
Yeah,
no electrical signal, that is the on state. And
yeah,
when you apply electrical signal, then it is the
yeah,
off state. Is it or reverse?
yeah. Actually, if we compare, suppose in a single waveguide, off state means no light is there,
Yeah.
and on state
So,
means light is there.
huh,
But
that is
here
okay.
in this directional coupler, output is the first waveguide, but what is happening is that we are comparing with the second waveguide. In second waveguide, on state
Yeah.
means light is there, off state means light is not there. In the second waveguide,
Okay.
if we say.
But here though it should be off, isn't it? Because there is no light here.
No, comparing to the second waveguide. Output we are taking the first
Oh,
waveguide, but yeah.
okay. Okay. Okay, I hope it is correct. Means that there was some confusion into my mind. That is why I asked here. Okay, you are sure about this results or this figure? I think
Yes, sir.
I would have request here. You should have given the intensity bar plot also, so that we can understand these are the higher intensity and blue colors are lower intensity. That is essential. In fact,
Yes, sir.
you might have seen in your paper. You might have given here is also it is essential. Anyway, so go ahead further. Any question in between? We can move further up to where we have read. This figure 3.5 we have covered or not?
Not, sir.
Okay, okay, you go ahead.
Okay. Okay, so let me start from figure 3.5. So figure 3.5a shows the transmittance of the device at different applied potentials over the entire C band. That is, C band is the wavelength range from around 1500 nanometer to 1580 nanometer. And figure 3.5b shows the extinction ratio ER insertion loss at on state and off state. The transmittance of the device over the entire C band ranging from lambda equals to 1500 nanometer to lambda equals to 1580 nanometer at different VG are shown in figure 3.5a. Also, the IL, that is the insertion loss of the device both at on state and off state, is shown in figure 3.5b. If we define the IL of the device as IL equals to 10 into log 10 output power by input power, the IL observed at lambda equal to 5050 nanometer for on state was minus 8.35 dB and for off state was minus 0.10 dB. The extinction ratio can be defined as insertion loss at off state minus insertion loss at on state. The extinction ratio at lambda equals to 1550 nanometer was around 8.25 dB for 300 nanometer waveguide width of SI device, that is WSI. Further, if the WSI is increased, the extinction ratio decreases because of the change in IL both at on state and off state. At WSI equals to 350 nanometer, the extinction ratio was around 2.2 dB. Therefore, in order to obtain a suitable ER, that is extinction ratio, we choose WSI equals to 300 nanometer. The modulation speed of the device can be calculated as reference 11 F equals to 1 by 2 pi RC, where C is equals to epsilon naught A by ds is the capacitance. Reference 51. Epsilon is the dielectric constant of HFO2. Epsilon naught is the permittivity of free space. A is the area of the device and ds is the thickness of the dielectric spacer. The device resistance was assumed to be 50 ohm. Reference 6. Therefore, C is equals to 265 femtofarad and F, that is the frequency, equals to 12.01 gigahertz.
Yeah, can you explain this figure 3.5?
Okay, the figure 3.5 shows the transmittance of the device at different applied potentials over the C band. Yeah, so here in figure 3.5a, what we have done is that we have used different potential. Suppose that here, as it is shown, we have applied 1 volt, 2 volt, and 2.3 volt, and we have applied no voltage. That is, we have applied no potential, and we have taken the reading of transmittance over the entire wavelength range, that is from 500 nanometer and 580 nanometer. So here, this green color indicates the green color line indicates the 2.3 volt, that is the epsilon near zero condition. So the value, that is the green line shows the value of 2.3 volts. So at around 1550 nanometer wavelength, so if we assume the line between 1540 and 1560, we will get the 1550 nanometer wavelength. So at this particular wavelength, we have got transmittance of around say around 4 like that, 4 3 like that.
What is the value here you have mentioned?
Value transmittance.
you should match whatever is written in text as well as what is shown in figure 3.5a. So here it is coming, I think, between 15 and 20. So it should be 17, 18, something like that.
Yes, sir. Oh, so this one I haven't written actually transmittance what I have got.
Okay. Okay. Should have been written.
Yeah.
This is E and Z condition. So very important kernel. This
Yes.
green one. Okay. No issue.
Okay.
But from here we can read. Okay. Whenever you are going to project, you should able to read it. Okay.
Okay, sir.
Yeah. Go
In
ahead.
figure, yeah, figure 3.5b shows the insertion loss at off state and on state. So the black color line indicates the off state and the red color line indicates the on state. So here for the on state, the insertion loss at 1550 nanometer was around minus 8.35 dB. And for off state, it was around minus 0.10 dB. And the blue color line indicates the extinction ratio. So this we have calculated from the formula insertion loss at off state minus insertion loss at on state. So we have taken the reading of each value at different wavelength for off state and on state, and from that we have got the curve for the extinction ratio in figure 3.5b.
Okay. Good.
So now coming to section 3.5, modified
What is the
sidewall link.
significance? One question can be asked: why you are trying to concentrate the results at 1550 nanometer? What is its specialty? Why we are going to design your device at 1550 nanometer only?
So because it is a low loss wavelength, the loss is around 0.2 dB per kilometer. The loss is very less as compared to other wavelengths.
Loss is less in the device or loss is less in somewhere else?
So loss is less, I think, in the device, sir, in the medium.
No, it is actually for long haul communication when we use fiber for transmission. The silica fiber offers least absorption or least loss at this 1550 nanometer because channel is there which provides least loss. So accordingly we designed your devices at the transmitter and the receiver so that you can utilize the channel's best part, because your device or circuits can be modeled. Their their loss or their loss uh, window can be shifted by by changing the dimension, we say width and height or other material. So this wavelength you can shift in your device while designing it. However, that cannot be changed into the fiber which is being used for the transmission purpose. And it is well established that at 50 nanometer, silica fiber gives almost zero loss. It is almost transparent. So longer distance transmission can take place if we optimize your device performance at 1550 nanometer. That is why 1550 nanometer has been concentrated more for communication purpose. For other purposes, we can design devices for other wavelength. But for optical communication or data transceiver, long haul communication or optical networking purposes, 1550 nanometer is the standard value. Another value is that 1530 nanometer, that is called zero dispersion. Why this zero dispersion is important? Because whenever we are increasing the data rate, there is a chances of overlapping. So because of the dispersion. So if you want to minimize the dispersion so that high data rate transmission can be takes place, we have to choose the 1530 nanometer or 1531 nanometer. But we have a solution in form of dispersion compensating fiber. So we put the dispersion compensating fiber after after silica fiber, which is giving loss, minimum loss at 50 nanometer. In this way we are achieving both advantages, means zero dispersion and zero loss at 1550 nanometer. So once this channel is long haul channel or intercontinental transmission a line is laid down or commissioned, so it means a heavy investment already has been done. So in order to exploit that transmission channels efficiency, accordingly we are designing your transmitter and receiver. So this is the reason. Otherwise the silica is almost transparent for 1550 nanometer wavelength, so giving very less loss. We can design even 1520 nanometer, 1400 nanometer. There is no problem as far as designing of this optical modulator is concerned. But issue is that to exploit the zero loss window available in the optical fiber. Is it okay, Himanshu?
Yes, sir.
Yeah. Okay, thank you. So you may now move further. If any questions coming into mind of our researchers who are participate here, can ask the question. If no, then we can move to this. This is central or most important part of this chapter 3, that is the modified sidewall angled silicon waveguide based electro absorption modulator. Over to you, Himanshu.
Okay, so coming to section 3.5, modified sidewall angle silicon waveguide based electro-absorption modulator. So introduction. Recently, plasmonic material-based optical modulators have drawn researchers' attention to design
Himanshu,
photonic. Yes, sir.
before going to this, can we have a break of 2-3 minutes for everyone?
Okay,
For
sir.
so for short break, 2-3 minutes. Okay. So it is 7:58. Let us meet at 8:02. Okay, because say for washroom etc. Okay, one can go and can join again. Okay, at least I am going. So this may be case for others also. Okay.
Okay, sir.
Thank you all participants for being here. We will have break for further 2 minutes. I think within 20-25 minutes we shall able to complete. This is very important. That is why there was a need of break so that we can refresh and can concentrate on this topic of modified sidewall angled silicon waveguide based electro absorption modulator. So earlier it was directional coupler based. Now it is a electro absorption. So only one waveguide is there. At one occasion it will absorb, on other occasion it will not absorb. So that is the basic working principle. So how to controlling that absorption mechanism through electronics. So that is the main thing. But here architectural design has been optimized as the chapter's name suggests, architectural design of silicon based optical modulators. So can we begin, Himanshu?
Yes, sir.
Okay, thank you so much.
Okay, so starting from section 3.5, modified sidewall angled SI waveguide based electro-absorption modulator. Introduction. Recently, plasmonic material based optical modulators have drawn researchers' attention to design photonic integrated circuits due to their efficient light matter interaction capability and compatibility with CMOS technology. Reference 25. Miniaturized devices integrated with plasmonic materials have led to a family of novel nanoplasmonic devices. Reference 3:25:55. The plasmonic materials such as ITO, vanadium dioxide, gallium dope zinc oxide, and graphene are index modulated materials in which the refractive index changes upon applied potential. Reference 53, 56, 57, 58. Various devices showing the electro-absorptive modulation in silicon waveguide coated with ITO, reference 6, 8, 9, 10, 15, and 59, and an ultra-compact EM modulator comprising TIN/HFO2/ITO/CU stack structure were previously demonstrated. Reference 60. The promising features of ITO, such as a unique ENZ condition and good electrical conductivity, has led to the rapid development of plasmonic-based optical modulators. Reference 53:55. When potential is introduced to ITO, the carrier concentration at the capacitively induced accumulation layer changes, affecting the effective mode index (EMI), which induces a loss in the waveguide. Reference 11. The device's EMI is varied by placing the active layer of ITO along with the dielectric spacer HFO2 hafnium dioxide in the SI waveguide, forming a SI dielectric SI stick along the direction of propagation of light. Reference 8 and reference 11. However, high insertion loss in the plasmonic material-based EM modulators is still a critical issue. Therefore, a new EM modulator with a high ER, low IL, and high FOM is highly desirable for photonic integrated circuits (PICs) and high-speed optical communication systems. Coming to section 3.5.2, design of the electro-absorption modulator. So here figure 3.6 shows the design of a modified sidewall angled SI waveguide based EM modulator. Here, the blue color indicates the silicon dioxide material, the orange color indicates the silicon material, and the green color indicates the plasmonic material, that is ITO, and the black color above the ITO material is the HFO2 dielectric material, that is hafnium dioxide, and the yellow color indicates the gold, which are there for biasing purposes. Now, the height of the silicon waveguide is 0.34 micrometer and the width of the silicon waveguide is 0.32 micrometer. Now, a new type of structural design is shown in figure 3.6. An EA electro-absorption optical modulator with ITO/HFO2 placed at an inclined angle between the SI waveguide is proposed. The SI ITO HFO2 SI is stacked upon a silica substrate. The majority of light is tightly confined around Si, ITO, HFO2, Si stack within the waveguide for transverse magnetic TM mode. The light ITO interaction varies the effective mode index EMI of the device. With a change in EMI, the IL of the device varies. To maintain a low insertion loss, the active layers ITO-HFO2 are inclined at a particular angle. The lower SI waveguide with sidewall angle at theta equals to 51.34 degree is 0.32 micrometer wide and 0.20 micrometer high. The thickness of the ITO is 2 nanometer. The metal contacts are placed hundreds of nanometers away for biasing purpose. The device can be fabricated using a hard silica mask and fluorine-based dry etching technique, reference 61 and 62. The deposition of HFO2 and Si can be done using deep UV lithography, reference number 11. Also, the overall height and width of the waveguide is 0.34 micrometer and 0.32 micrometer. Coming to section 3.5.3, results and discussions. The optical characteristics of ITO for the device can be calculated from the equation 3.1, 3.2 and 3.3. For the modified sidewall angle SI waveguide base EM modulator, KHFO2 equals to 25 is the permittivity of HFO2 and THFO2 equals to 5 nanometer is the thickness of HFO2. TACC equals to 2 nanometer is the accumulation layer thickness and N0 is the bulk free carrier concentration of ITO. Under zero bias gate voltage, N0 equals to 3.0 into 10 to the power 25 meter cube. Reference number 11. Also, the complex permittivity and refractive index of ITO are shown in figure 3.7a and b. Figure 3.7a shows the permittivity of ITO as a function of carrier concentration. The real Re epsilon ITO and the imaginary part Im epsilon ITO of ITO's permittivity have been derived from equation 3.1. So here figure 3.7a shows the complex permittivity of ITO, that is the real and imaginary part as a function of carrier concentration n at lambda equals to 1.55 micrometer. The inset shows the carrier concentration n as a function of the applied gate voltage Vg. So previously we have seen the change in real and imaginary part of the permittivity of ITO as a function of voltage. But here in this figure, we have shown the change in the complex permittivity of ITO, that is the real and imaginary part, in terms of their carrier concentration. In terms of their carrier concentration. So with increase in carrier concentration, the real part of the permittivity of ITO decreases and the imaginary part increases. But at around 6.45 into 10 to the power 26 meter cube, we can see that the real part of the permittivity tends to reach zero, which is known as the epsilon near zero condition. So at this concentration, that is 6.45 into 10 to the power 26, the material property of ITO changes. So this carrier concentration of 6.45 into 10 to the power 26 corresponds to a particular potential. So in order to show this relation of carrier concentration and potential, the inset of figure 3.7 is shown. That is showing the relation of voltage, that is the applied potential, and carrier concentration. Now coming to 3.7b, it shows the refractive index, which is affected by carrier concentration. So it increase in carrier concentration, the refractive index of ITO changes. And the black color indicates the real part of ITO and the red color indicates the imaginary part of ITO. So the inset shows the change in carrier concentration of electrons with respect to applied gate voltage Vg. So in figure 3.7a, we can see the permittivity which changes with change in carrier concentration, and the effect of carrier concentration on the refractive index is shown in figure 3.7b.
Yeah. So
So
this
the
is
inset,
continuous characterization. Yes.
okay, the inset shows the change in concentration of electron with respect to applied gate voltage Vg, which have been calculated from equation 3.3. At Vg equals to 4.45 volt, the electron density observed was N equals to 6.45 into 10 to the power 26 per meter cube. At the ITO HFO2 interface, the electrical properties of ITO change from a dielectric state to a pure metallic state at N equals to 6.45 into 10 to the power 26 per meter cube, when the real part of ITS permittivity reaches zero. This is termed as ENZ condition. The effect of Vg on the carrier concentration in the ITO layer was investigated by the Thomas Fermi screening theory, reference number 59 and 60. The real and imaginary part of the refractive index of ITO is plotted in figure 3.7b. The refractive index is dependent on the permittivity of ITO and can be calculated as epsilon r equals to n minus ik whole square, where n is the real part of this Re and ITO and k is the imaginary part Im and ITO of ITO's refractive index. The refractive index of NHFO2, that is hafnium dioxide, is equal to 1.98. Then NSI, that is the refractive index of silicon taken, was 3.47, and NSiO2, refractive index of silicon dioxide, was taken as 1.44. And NITO, that is the refractive index of ITO, as plotted in figure 3.7b, were used to calculate the EMI of the device. Figure 3.8a and b shows the propagation of modes inside the waveguide. The majority of light is tightly confined at the ITO-HFO2 interface in TM mode, whereas in TE mode most of the light gets diffracted throughout the stick because of total internal reflection. So in figure 3.8a and b, we can see that figure 3.8a indicates the TE polarized mode for the on state and off state, and figure 3.8b shows the TM polarized mode for on state and off state. So in on state, we can see the light in the waveguide. It tends to if it tends to leave the waveguide throughout the side of the waveguide, but in off state, all or most of the light is absorbed in TE mode. Whereas in TM mode, if we can see that most of the light is absorbed by the ITO-HFO2 layer in off state. In this figure, we can't see it because the figure is very small. And in on state, most of the light is allowed to pass. So here the TE mode and TM mode is shown for the device. Moreover, with an increase in applied Vg, the carrier concentration increases, which lead to ENZ condition, where the majority of electromagnetic energy inside the waveguide is confined in the accumulation layer, reference 5263. These affects the EMI of the device, where the real part affects the phase of polarized light termed electrorefraction, an imaginary part or mode power attenuation MPA refers to electroabsorption, which corresponds to the transmission loss in the waveguide. For the modified sidewall angle design, TE mode almost follows similar trend to TM mode as shown in figure 3.9. But MPA is not very prominent in TE mode as most of the energy gets diffracted throughout the stick. The MPA for TM mode increases rapidly with an increase in carrier concentration because of the ENZ effect and reaches the peak value at 6.78 dB per micrometer at 6.45 into 10 to the power 26 per meter cube. With further increase in carrier concentration, MPA decreases rapidly as it is dependent on the refractive index of ITO. The MPA is dependent on the Vg and the thickness of accumulation layer. with a higher with a higher thickness of the accumulation layer, the gate bias voltage has to increase to reach the ENZ condition. However, there is a possibility of HFO2 layer breakdown, so the thickness of the accumulation layer was set at TACC equals to 2 nanometer, reference 11. Thus, the effect of different waveguide width and different sidewall angle theta on MPA have been investigated. The effective refractive index RE, NEFF, and MPA for TM mode of the waveguide changes with an increase in carrier concentration as shown in figure 3.10a. The MPA decays exponentially and as n deviates away from 6.45 into 10 to the power 26 per meter cube at Vg equals to 4.45 volt in both the direction, because if epsilon r shifts away from its minimum value, the optical power in the accumulation layer minimizes and is redistributed to the HFO2 and Si layer. The MPA can be calculated as minus 10 log 10 output power by input power at n equals to 6.45 into 10 to the power 26 per meter cube, that is off state. Maximum MPA was observed, and at n equals to 3.10 to the power 25 per meter cube on state, minimum MPA was observed for the TM mode. Also, RENFF varies around the ENZ region as it is dependent on ER. To investigate the effect of sidewall angle on MPA, different sidewall angles were taken for the waveguide as shown in figure 3.10b. The sidewall angle affects the field confinement in the slot region of the waveguide due to light ITO interaction at different angles. Although, although the maximum MPA for the offstate has been observed around theta equals to 45 degree, we choose theta equals to 51.34 degree to maintain a balance between ER, MPA and FOM, which is the optimum value. MPA of 6.78 dB per micrometer has been observed for the device at theta equals to 51.34 degree in off state. At on-state, MPA ranges from 0.015 dB per micrometer at theta equals to 30 degree to 0.0136 dB per micrometer at theta equals to 60 degree. To study the effect of SI waveguide with WSI on MPA, WSI is varied from 0.2 micrometer to 0.5 micrometer for both on-state and off-state. The maximum MPA for the off-state was observed to be 6.78 dB per micrometer at 0.32 dB, and for on-state it was observed 0.016 dB per micrometer as shown in figure 3.10c. The effect of wavelength lambda on MPA over the entire C-band for both on-state and off-state is shown in figure 3.10d. Now, the effect of thickness of ITO and HFO2 layer on the MPA is shown in figure 3.11a. Smaller thickness of HFO2, that is 5 nanometer, leads to an increase in MPA due to high charge accumulation and subsequently confines the electric field in the ITO layer. Also, the effect of change in the SI core refractive index on MPA is shown in figure 3.11b. At the normal refractive index of SI 3.47, MPA of around 6.7 dB per micrometer was observed for the off-state and 0.016 dB per micrometer was observed for the on-state. The ER and FOM can be calculated from the on-state and off-state losses of the modulator as given in equation 2.13, 2.14, chapter 2. FOM is a crucial parameter to measure the balance between ER and IL, which can be calculated from equation 2.14, chapter 2. The FOM of the device was 422 at 1550 nanometer application wavelength as shown in figure 3.12a, which shows improved performance compared to ITO-assisted EA modulator shown in table 3.1. Also, the MPA was calculated over the wavelength range from lambda equals to 1.20 micrometer to lambda equals to 1.80 micrometer to find the full width half maximum wavelength for the device. The full width half maximum wavelength was observed to be in the range of lambda equals to 1.45 micrometer to lambda equals to 1.68 micrometer, resulting in a
Supporting
supporting
bandwidth
bandwidth
of
of 230 nanometer
uh,
as shown in figure 3.12b. The modulation speed of the device can be calculated from equation 3.4 and was found to be 231 GHz, and the capacitance was 1.37 femtofarad, calculated by electrostatic analysis performed with FEM method using a commercial solver COMSOL multiphysics. The resistance R was assumed to be 500 ohm, reference 9. Also, the EBIT was calculated with using equation 2.15 chapter 2 and observed to be 6.8 femtojoule per bit.
yeah, let us read the summary also, then we can discuss
Okay.
little bit. Yeah.
3.6 summary. A summary of this chapter is as follows. Section 3.1 gives a brief introduction to the chapter and how the chapter has been organized. Section 3.2 discusses and gives a brief introduction to the plasmonic materials. The various numerical methodologies used to carry out the simulation results are discussed in section 3.3. Section 3.4 gives an introduction to directional coupler based optical modulator. It discusses the material characteristics of ITO and the architectural design of a directional coupler based optical modulator. Section 3.5 discusses a new type of design for EM modulator based on modified sidewall angle SI waveguide. Also, the performance of the device have been evaluated in terms of ER, IL, FOM, and EBIT.
Yeah. Thank you so much, Himanshu, for reading and taking so much pain for reading line by line. But it's good that we have gone through. And uh, just a second. This is the table which shows, a gist of this last section. You see the work done by Himanshu. This is the last one. That is the modified sidewall angle is compared with other existing modulators reported in the literature, that is say this nanowire based hybrid plasmonic, this gold slot based, this tin based, the silicon ring, the reconfigurable hybrid, and then ITO. So many modulators were already there. So his modulator is finding a place among them. It is in many aspect it is superior, in many aspect it is comparable. So which is mentioned in the remarks. So this kind of requirement is essential to get your work published. So this is one thing. And second thing, you can see in these different curves, in that the work has been extensively, means from all dimensions, your parameter have been proved, so that there should be no scope for any confusion. Okay, so Himanshu, can you give the link of this published paper in our chat box in a quick time? It is
Okay, sir.
available.
Let
Yeah,
me check.
yeah. So that those who are participant can read the original one, which is published in this Journal of Optic, which is the last section. And I'm very happy that all participants are here with showing lot of patience, because again as I told you earlier, reading a thesis is really boring task, that to a very high technical level. Only peers used to read, but here we are trying to, as time and again I'm telling, we are trying to change the culture, we try to build up, so that first time you are hearing these many words, next time if you will hear again, you will come to know in a better way. And we are trying to stimulate, you are trying to stimulate your brain, you are trying to feed some new terminologies related with this optical modulators, optical communication, silicon photonics, characteristics, so that you should be aware what are the expectations. So the what are the expectations from the researcher, and how it comes as a thesis, how to report your outcomes. Doing the research is one aspect which is very very important, but how to represent, that is an art. Doing research may be very technical work, but how to write, how to represent your outcomes, that is very very important. Many times we used to work as Likinti and Sufayo will be agree with me that they have done the task, but they could not come up to the level where they can report their results. So this is also an important task, the way doing the research work. So nowadays you see many commercial people have come up, okay, to provide the assistant for publication of the work, article publication of the thesis, because they understand that writing a thesis, writing an article is required a different kind of skills beside whatever we do as a researcher. So from there, and reading also. So, sometimes we publish the work, but very few people used to read. So that is also a discouraging aspect here. So through this exercise, whatever we are doing, PhD reading session, through this exercise, we are trying to go through, try to appreciate at least within our limited people of lightweight communication system, and few more people have joined. If I will be happy if they can introduce, that shall be great. Particularly those who are new, uh, we are not aware, like Navneet Kumar, can you unmute your microphone and introduce yourself? It shall be nice to hear you. Navneet Kumar, can you hear us? To me, others are don't. Otherwise, okay. Mehmet is in IT department. Mehmet,
Yes, sir, I am.
yeah. Can you introduce? Because others are from our light wave communication system laboratory. Yeah, Mehmet, over to you. You just introduce
Sure,
in
sir.
one line.
Hello, everyone. Myself, Mebante Salhe from Jawai, Meghalaya, and I'm currently studying in Nehu for the third semester, which is obviously IT department.
Yeah, nice to hear. Even BTech third semester student is showing, or learner is showing the interest in the thesis. So we can imagine what kind of goal he might have set. Okay, so sometimes in Hindi there is a saying called "Hon har birwan ke hot chikne paat," means those who wants to achieve high goal, they show their kind of indicator at very beginning. So yeah, thank you, Mementai. Welcome.
Thank you, sir.
And here we have Pinsuk. Just say a few words. Pinsuk Lang, can you hear me? Then we have yeah,
Hello,
Pinsuk.
sir. Hello, everyone.
Hello.
I'm Pensuk Langwanyang, and I'm from the third semester of MTech from ECE department.
Yeah, good. Thank you. Bhasha Jyoti, within 30 seconds you can introduce. Bhasha Jyoti, can you hear? Bhargavi, Mansi, Mansi Das.
Yes, sir.
Yeah. Over to you. It seems there is a network problem from Bhargavi. Yeah, Mansi, just tell which semester from
Sir,
where.
can you listen? Sir, am I audible, sir?
Yeah, very much.
Yes, sir. Yes, sir. So, hello everyone. My name is Bhargavi Priyama Bora. I'm from Guwahati, Assam, and I'm currently in the fifth semester undergraduate.
Great. Thank you, Bhargavi. Mansi, over to you.
Hello everyone, I am Manashi Das. I'm from Guwahati, Assam, and I'm currently studying in the fifth semester of Electronics and Communication Department, NEHU.
Great, great. Yuvraj,
Good
YMR, yeah,
evening, everyone.
good.
I'm doing nanotechnology, MTech, third semester.
Great, great. Indrani,
Good evening, everyone. My name is Indrani Paulroy. I'm from West Bengal, Calcutta, and I am a student of the Department of Electronics and Communication Technology in the third year.
great, great. Thank you.
Thank
Likinti,
you, sir.
Likinti
Good
Bandri,
Yes, sir, I'm here. Good afternoon, everyone. Oh, good evening, everyone. I'm Likinti Bandrityoso. I'm from Lightwave Communication System Laboratory, and currently I'm doing research on this, sir.
thank you, Likinti. And next, I would request again Navneet Kumarji. Can you hear us? So maybe some issue. Anyway, I think we have covered. Anyone left? If not, so thank you so much again. This marathon journey of reading these chapters. So this is the contributory chapter, chapter 3, and little bit heavy chapter
So
also.
I had a question regarding one of the topics on the paper. I
Yeah,
was just
sure.
wondering about the diagrams that have been cited in the paper.
Yeah.
Are they being directly taken from the reference material, or did or was it was it was a reproduction rather than just citing the
Himanshu,
material directly?
Himanshu, over to you.
Yes, the diagrams in chapter 3, which we are reading today, are solely work of Lightwave Communication Laboratory, whereas the diagrams in previous chapter, chapter 2, they were taken from the references.
Okay,
All the
so I
diagrams,
mean, it was a direct reference, nothing. I mean, it wasn't reproduction, or maybe that it just worked on it in a new way, just directly, and not directly referenced it in the previous chapters.
yeah, previous chapter 2, they were actually, we have taken references, but the thing is that directly we didn't took it, we actually drawn it from outside. So direct
Okay.
representation is not there.
So how did you do it, if you don't mind me asking? I mean, how did you reproduce it? What was the method, or what were the software or tools that you used when you went to redraw the specific diagrams and the reference materials?
For diagram, virtual softwares are there, and we can also make it in PowerPoint or Words or MS Paint. But virtual is there. Windows, the tool, I forgot the name. Windows virtual tool for drawing, like that.
All right. Okay. Thank you very much.
Okay.
Very good. Thank you for asking the question, Indrani, and to
Okay.
Himanshu, thank you for giving the answer. Anyone else? Actually, curiosity should be there to know something. Forget about that we are going to ask any silly question, etc. Okay, there's no as such silly question. Okay, so if not, then again, thank you so much for being here, and thank you so much, Himanshu, for taking so much pain. In fact, I was little bit trying to tell you, okay, have some, water, etc., because it is reading, it exhausts you also. So thank you for your patience and putting a lot of effort, but definitely it is going to give you, you know, benefit in near future. So with this, let us conclude. Thank you so much again. And please come tomorrow, same time, same place, same method. Thank you so much. Good night.
Thank you,
Take
sir.
care.
Thank you,
Thank
sir.
you.
Sir,
Thank
thank
you.
you,
Thank you, sir.
sir.
Thank you so much. Bye.